All right. Good afternoon, everyone. Let's get started. Okay. Let me just do this. All right. Hopefully this is a little bit better. All right. Let's start with some administrative stuff. So first of all is the change in help hours. We made some changes, so please review them either on the website, or if you go to the syllabus, you can find information about when the office hours are happening in communication. Last Monday, we said we are going to be available after, but we missed, it was my fault. I recorded the wrong room, so we were kind of looking between rooms. So if you have been waiting for us and then gave up, apologies for that, and we should be there when we say we will be there in the future. All right, so please check that out. Last time you also had lots of questions about how to form projects, and to help you out with that, we had started basically these groups where you can assign yourself to any of these groups. I think just a moment, I'll go into your view because it's slightly different from mine. So here, if you go to groups, so under people groups, you should be able to select a group. Here it looks like I cannot do it, but another student had confirmed that they can do it. So I believe you will be fine with just picking a group randomly. Other option is to go under discussions, and there is an official thread for forming projects. So here you can also post some of the students who have already written something are good examples of what to write here. You can say what your interests are, what you would like to work on, and maybe some other people will be interested in the same things. So there are these two options, and eventually, if you didn't form any team, you didn't assign yourself to any group, we will just assign you randomly into groups of 3. Related to groups, someone else had asked, is there a difference between grading undergrads and grads? And there are no differences in how we approach grading. That said, if you are forming a group and you want to emphasize, you must emphasize who will do which component. If the component that an undergrad student will do is smaller than the component that a grad student would do, is fine with us. But this is something we will kind of check when we look at your proposals. And if we deem that something is too small, we will also, of course, let you know and you will revise it. You also ask for examples of projects, and next time I should come some physical posters here so you can check them out and see what kind of projects are suitable for this course. All right, there was also a question about how to navigate this calendar, so I will just quickly go through that. So here, after each lecture, I will link the recording. So here is, for example, the recording from the last time. And then slides will be basically what I will write in the lecture today. So last time we had actual slides, but today I will write here, and then I will turn this into a PDF, and you will see that. And the notes are what has been written by the previous professor who has previously taught this course. So if you click on the notes, you will find those notes that I basically use to prepare the lecture. And just to emphasize, recording and slides will be available only after the lecture. So if you click now on any of these, you will just get the website again. All right. Next big announcement is that the first homework is due, which you should be able to see, and I sincerely hope this works out. It works great. just go under assignments, and then you have A1 statistical principles. Here is a PDF of the problem set, and then here you have two files that you can use to write your solutions in LaTeX. So you just don't download these two files, put them in Overleaf, compile, and you will get the PDF out, and you submit that PDF again in Canvas. I just also want to make a note that these homework assignments are designed to help you really learn the material that we are covering in these lectures. And if you really work on them on your own, you will probably have no issue with midterm and final exams that will be done in person on paper. So yeah, I suggest you that you really take this homework seriously and use them as an opportunity to really learn the material we are teaching here. All right, and I believe that's almost everything. The last thing I want to talk about before going into the lecture is one of these policies that I said I will go over every time. Yeah.
My eyes are kind of
sure. So this can also go into. All right, good. Great. So I'll just read one of these policies, and every time I will do this such that you know all of the information in the syllabus. So here we have online student expectations. Though the online format allows students great flexibility to complete their work, this course has have a structure and timeline. As such, the following accepted of all students in this class. Students must be self-motivated, organized, and willing to stay on top of their schedules. Students should take control of their learning while in this course. Students are expected to follow the core rules of etiquette at all times while participating in the class and communicating with others. Students will log into the course a minimum of 3 times per week. Students are not expected to interact with their classmates in person.
It's for the online course version.
Okay, gotcha. All right, sorry, I didn't realize that before. All right, then this doesn't really apply because now we moved into person. Sorry, I should have really read this beforehand. All right, so then we should go into COVID campus guidelines. I believe that here you should just know that there is this website and there are all this information. I believe this information are not regularly updated. So for example, it says that actually this refers to University of Utah health facilities. So if you go to a doctor, you still need to wear a mask. But as far as I know, in the buildings and here, as you see by all of us, you don't need to wear a mask. You can find another information here, such as vaccination, any guidance you might need, and so on. So yeah, please refer to this website if you have more information about this, and there are also other resources here. And my only expectations regarding this is if you are feeling really sick, I would ask you to look at the live stream instead of coming here in person. You will probably get very similar experience, and it will probably be better for all of us to do that. All right, any questions about this? Yeah.
About this, are there any?
No worries. We should move on, or?
Are the materials in the foundation book necessary to that?
No, the foundations, the book is more comprehensive than what we are actually going to cover in the course. So we recommend that you read those readings, but probably the readings will include more information than what will be covered in the lecture, and also what will be required from you in homeworks and in exams. Especially for homeworks, if there is anything specific in the book we think you should look at, it will be referenced. Yeah, it's quite a lot of reading, so I understand reading everything might not be feasible. Okay. I think this is it regarding the administrative stuff. Okay. Oops. Okay. So let's move to the lecture. Yes, all right. Okay, let me just see how can I come back here. Right. I'm trying to make this window a little bit larger, and I will move this to make it less distracting. All right. If this is too small, let me know and I will try to fix it. All right, so the goal for this lecture today is to revisit some basic high-level statistical principles, and we will do that through hashing and examples of random processes and kind of associated behaviors that come from these processes. And the reason why we want to go through this is because this exercise will be useful for you to think about these probabilistic and randomized algorithms, those algorithms that include some degree of randomness in their logic and processes. So we are going to start with the first principle you should know, and that's IID assumptions. All right. How many of you have heard this term before? Can you raise your hand? Quite a lot of you. This is great. And I think it comes from the fact that machine learning is becoming more and more mainstream. And this is one of those core principles that everyone needs to know. So what IID stands for is, first I is for independent. And ID here stands for identically distributed. And what these things mean is that you have some kind of data set you are going to work with, and this data set has some data points. And independent means that some of these 2 points, xi, xj, are going to be independent of each other. And identically distributed means that this xi and xj come from the same distribution. And sometimes when we mention this assumption in machine learning specifically, you might hear a slightly different version where under identically distributed, you might see something like, okay, if we split this data set into our train and our test set, then our train and test set will be equally identically distributed. So we can have the train, it will be equally distributed as the test. And why do we care about these assumptions? There are at least 2 reasons for them. In the context of machine learning, when you have the train set and test set being equally distributed, then you can tell something about expectation of how the training error will, how similar the training and test error will be. If they are identically distributed, you can expect they are going to be similar. So why? One is to study relation between test and train error. And the other reason is that this fact that these data points are independent enable us to optimize more efficiently. Specifically, we will have something like calculating the joint probability of endpoints given some parameters. And then if these points are independent, then we know that this equals to their product of individual probabilities. And now when we apply logarithm to this, we know that this turns into a sum, right? And this sum is way easier to calculate. So these are some common reasons you might see why this IID assumption is important, but you will also see throughout this course that when we bring some kind of theorem or some kind of formula for expectation, that we will also base it on the assumptions that these things are identically distributed and independent of each other. Do you think this is a valid assumption? I will try to. For some reason, this doesn't work, which is a bit annoying. Okay. Sure, but it won't make it wider. And if I can make the window wider, I can kind of zoom it here on iPad. Is this any better?
No.
Yeah. It's not.
Pretty bad assumption because I can't assume that. I mean, I can assume that the previous result is not affecting the result of the next one, which depending on what you're doing,
That's a perfect observation, and you are entirely right. This is assumption we make, and it makes mathematical framework neater and allows us to do stuff with it. But is it a valid assumption always? It is not. So an example where it is valid assumption is if you roll a dice, for example, what you get in one turn is independent of the other. But for example, if we are trying to generate text, we know that what we have generated so far influences what we are going to generate next, right? Because language has structure and grammar. So this is not always a valid assumption. And because we sometimes assume it, but it's not valid in practice, it can result in issues. And those errors that we have mentioned last time when we said we will have these algorithms and they will come with certain errors, and we have to understand whether those errors are acceptable or not. Great. Yeah.
What is theta in like?
Oh, here, this is it's not really important for what we are talking about right now, but if we are looking at, let's say, machine learning and some kind of classification problem, usually we would have certain parameters of the model that we are learning to solve the task. So, for example, if you're learning polynomial, the weights of the polynomial that can give you a solution to a problem.
So it's like the x is given the model.
X is given, X's are the data points, and given those data points, you're trying to estimate theta. Again, this is not really important, so let's not spend too much time on it. More important point here is that if you are assuming independence and you apply the logarithm to it, you turn the product into sums, and that helps you to have more efficient optimization. So this is a place where this kind of assumption is really, really useful. Okay, so we are going to shift gears a little bit now and introduce some of the notation we'll need for this lecture. I will try to write bigger. All right. So this is specific to this lecture. So we are going to start with some data set, x1 to xn. And this is going to be IID data set, which again means that these data points are independent and independent and identically distributed. And each one of these xi's is going to be an integer from 1 to n. And we are going to denote such set like this. So every time you see this, it means it's a set of integers from 1 to n. Okay. And this symbol means that this element is part of that set. And this is a definition. So what are some examples of n, of this set of integers? It could be all all possible words in a dictionary, for example. And this is something you will see commonly in natural language processing, where you will have a vocabulary of all the words in English, and each one of these words will be associated with an integer. Not only that, we are going to break those words into subwords. So we are going to have actually a vocabulary of all possible subwords that are commonly used in English, which is usually 30,000 of them. And then each one of them will be represented with an integer. But it can also be other stuff, all possible IP addresses, or birthdays, and so on. And you might wonder, why are we presenting these things with like this, with a set of integers? Why don't we just make a set of actual strings? And the reason in the nutshell is for simplicity. This will allow us some notational and implementation possibilities, basically. So it is not necessary to do it like this, but it is convenient to do it. And also today, we are going to assume that the probability of each one of these xi equals to an integer is uniform. So for every possible integer, the probability of this data point being assigned this integer is equal. Okay. So again, similarly to IID assumptions, do you think this is realistic? Yeah, yeah. So again, my question was, we are assigning uniform probability to every possible birthday. Is that realistic? Okay, I see some head shakes, which is a correct answer. It is not realistic because we know that some birthdays are, for example, more frequent than the other ones. So if you look at the data statistics in the US, you will see that summer is the most frequent period of birthdays. So it is, again, not a realistic assumption, but it is the one we employ. So not always. And I keep mentioning these assumptions that are not always true, because it is important to embrace that a lot of times when we are dealing with these mathematical frameworks, we are using assumptions that might not match what you are working with in the real world. But for today's lecture, that's what we are going to work with. So now,
Can you say the thing you wrote next to the day again, just in English? I'm just trying to get the notation. So
yeah, we can go through it slowly. So this is a probability that a data point here, xi, equals to an integer j equals to 1 over n, where n is number of the integers we are working with. So it means that every integer in this set has equal probability of us assigning that data point to that integer. And if it's not in the set of 1 to n, the probability equals to 0.
So I noticed an issue here. If you like assign an integer to like words in dictionary, you find ordering and then suggest like you map with these words when they obviously have no meaning. So do they still? I mean, like, how do they go about that problem? Like, you assign numbers to words, so they don't really have any tactile ordering.
I can tell you what happens in NLP concretely. Is this the question you're looking for? Like, is the question, once we are assigning the number to a word, what do we usually do with it? Is that the
Not
question?
because of like word doesn't really have.
Yeah, that's true. I mean, this what we are going to kind of get into now is hash tables. So this way of representing these things gives you just a way to index them. So in NLP specifically, what you would do when you are assigning these words, so we would have your vocabulary of size, let's say 30,000. And then you will have values for 1 to 30,000, but this first index might relate to the word, I don't know, dog. And then you will have another matrix which has equal number of rows as there are words in your vocabulary, which is 30,000, but it has some very high dimension D. And then knowing that dog is assigned index 1, you are going to retrieve the first row here, and that's going to be vector representation of your word dog. So this is how this is used in NLP. Yeah. But yeah, let's not go more into that because that's a whole other topic. All right, so as I said, the point of this class is to go over some of the principles you will need to think about these probabilistic algorithms, and one of them is hash table that you have probably seen before. It's a data structure you have seen maybe in CS 24-20, I believe is the name of the course. So this is more what we are going to go through now is more like a review of hash tables. So first of all, it's a data structure. But the most important component and the one that's most interesting to us in this course is hash function. All right. And to define a hash function, we need a family of hash functions. And then we are going to draw or sample one hash function from this family randomly. So small h is going to be element of this set of all of these possible hash function. And it's going to be randomly drawn. So when we say a random hash function, the random part is connected to the fact that we are randomly selecting this hash function from the set of all hash functions. But the function itself is deterministic. So we will say that this hash function goes from some set of all possible strings of length k. So capital sigma k denotes a set of all strings of length k. And one concrete example you might see in these textbooks is sigma k that's consists of zeros and ones of length k. So strings of bits of length k. All right, so this was a little digression of what sigma k is. This is going to be our domain for hash function h, and we are going to map it to, again, that set of integers from 1 to n. And this function is going to be deterministic. So don't confuse with what is random here. Hash function is not random. The choice of hash function is random. All right, and one of the important properties of a good hash function is uniformity, which means that you want to assign, you don't want one element, one integer to be assigned lots of data points. If that had happened, then all the benefits of doing hashing methods will not be achieved. Basically, the efficiency won't be there. So one important property is uniformity. And again, using the probabilistic notation, we would write that probability over the hash functions, that the hash function of some string is equal to the hash value of the other string is again equal. All right, so just repeating that again, the probability over hash functions that a hash value for one string equals to a hash value of another string is equal to 1 over n. So if we have that, then all of these positions in from 1 to n kind of have a same chance to get elements assigned to it. And that will kind of give us this uniformity that we don't have certain values, certain integers having too many values associated with them. All right. Another thing important to mention here, which I kind of said now informally, is the concept of collision. And that's when a pair of strings are assigned the same integer, a same hash value. And basically, you don't want to have too many of such collisions, as I said, because then one hash value will have too many elements associated with it. So one thing you might be wondering about is, okay, I get that, I get this mathematical notation, but how do I go about this point of choosing the hash function? So let's see what are the options you have. So one option is to use whatever is built in Python. Oh, sorry. And one such hash function is called SHA-1. And what this particular example is doing is giving you the following hash values. It's calculating some kind of SHA function, but it's concatenating certain string with the string you are given it. And this is that random part. So you can sample different strings A here to get different hash function here. So that's why we have this special subscript A here, because we have this additional, you can think of it as a parameter that we are kind of associating each of these hash functions with. All right, and the string age is also is just a string of certain length L, and you can call it a seed string. But this concept is also known as salt. Okay, so that's one option. The second option is multiplicative hashing, where again you have a parameter age A, and here you're going to take a floor function of n times fraction of x times A, where floor is, for example, if you have 23.15, floor will be whatever is before decimal, and the fraction part will be everything that's after the decimal. And this is again what is known as salt. And it is suggested that this is some kind of a big integer number that has in its binary form like a mix of zeros and ones. Basically, you want to avoid having a number that's power of 2 here because it might cause some instability issues. And then maybe the most common one you have seen is modular hashing. Unlike these other ones, it's just HX X mod M, so has no associated parameter A with it. And there are reasons why this, despite being very commonly suggested as a hashing function, is actually not a good hashing function. So the first problem is that if you take two numbers that differ by 1, they will always have different hash value because the modulo will always be different. But then if you have numbers that differ in m positions, these will always have the same hash value. So this hash function has too much structure, and therefore it is not a great choice, especially given these other options that you have. That said, you might see in the literature variants of this modular hashing that kind of try to fix some of these issues. For example, they use a large prime number for instead of m that is still smaller than m. Then you have a little bit less regularity, but it's not a great option to use. I'm sorry for blowing into the microphone. All right, so far we have seen some of the annotation that is going to be important. We have talked about IID assumption, and we have covered what are hash tables and hash functions, and so some examples of them. Now we are going to go into some more concrete random processes and try to analyze them and get some observations that might be useful for us. Are there any questions so far? All right, yeah, this is a little bit straightforward. Yeah. Sorry, second? Sorry, for what? For string? This one. Yeah, that's a good question. I'm not sure. Yeah, I would need to come back to you about that. I mean, I can understand why are you asking this? What would be the floor and fraction of a string, right? Yeah.
This is the first bit. Maybe elaborate a little bit on A, because you're saying that A is randomly, but so this is different from randomness of collecting the 8 on the set of the big 8, right?
Yeah. So let me try to be more precise. Basically, by using A, you can construct a family of these different hash functions with these, specific formulation, and then you can pick one randomly. So the choice of A is not random. You can pick as many, like you can have many options there, and you can maybe construct them from all the possible strings of the length L. So there doesn't even need to be randomness there. A is another string. Yeah, that's right. Yeah, here you have, I denoted it as A is element of a set of all strings of length L. Well, L is that, maximal length of the prefix you want to have. Okay, let's move forward. I think the stuff that's coming up is slightly more interesting. So we are going to work with a concrete example here. We are going to have some as an input sequence of m distinct strings. So this is how I will denote sequence of strings. So I will use the same brackets, but I will have here a subscript and superscript. So this is a sequence of m distinct strings So SI is different from SJ. We'll have assume some hashing function here that puts these strings into integers from 1 to n. And there is this very general question that might arise, and that's that how many strings we need to see until we get collision. So this is one general question, and maybe another way of saying it is like, what is the expected number of strings we need to see until we see two equal strings? And this broad question is actually has a concrete problem associated with it, which is called birthday paradox. And birthday paradox says that if only approximately 23 people are in a room, then the probability of a pair existing that has same birthday is larger than 0.5. Can someone tell me why is this, what is paradoxical about this? Would you expect? Oh,
Probably 365 days a year. Well, only 23 people.
yeah.
There's no chance I don't think that's match, but
Yeah, exactly. That's the correct answer. So here, what is paradoxical about this is that 23 is way smaller than 356, which is the usual number of days we have in one year. Have you ever been in a class where you simulated this birthday paradox? Can you raise hands? Okay, just a small number. Let's try to do that for the fun of it, to compensate for a lot of math notation in the beginning. So what we are going to do is to try to see how many of you are going to ask for your birthday until we reach a point where we found two of you that have the same birthday. All right. All right. All right. Maybe we can start with our DAs. 24. Okay. Make. Ooh. August 18th. Right? Maybe December 11th. April 19th. May 27th. Sorry, you want to go next? 7th. Right.
November 22nd.
November 22nd. Okay.
February 27th.
Sorry, a second.
February 27th.
February 27th. All right. I think in the second row we stop somewhere. I think you're next. August 22nd. All right. March 1st. Okay. February 13th. You go there. June 18th. Right behind.
July 27th.
July. All right. Maybe we can go like through third row. October 13th. May 14th. Oh, this is taking a while. We are an Emily. Right, maybe I'm gonna. June 19th. So close, yeah. September 28th. Okay, third row. You can go next. April 4th. Okay, maybe now here. I can't believe this is taking so long. September 1st. May 4th. Maybe here. March 8th. Oh no, so many first weeks left. May 21st. Okay. 14th. Oh, 14th, yeah.
February 19th.
Okay.
July 7th. March 16th.
You have the, all right, yeah, thanks. I really appreciate it. All right, so we will learn another lessons through this exercise, and that's that we are dealing with random processes. So there might be certain expectation, but that doesn't mean you are always going to be close to that expectation, which happened kind of here as right now. Let's see how many trials we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. All right, we had 30 trials, while our paradox is saying that there is if we have seen 23 people, there is 50% probability that this is going to bring us collision. So in a way, it's not super far away, but maybe if none of you had conflicts and only at the end we reach out to the person who had, this would be like a serious anomaly. Okay. So let's try to derive this more formally. And just to kind of remind you, maybe this is too fun and now you forgot what the question was. The question was, how many distinct strings until collision? And a concrete example of that is, given all the birthdays in a year, how many people we need to see until we reach 2 people who have the birthday on the same day. And we want to find a more formal way of saying that this that we need 23 people to achieve this probability. So that's what we are doing right now. So what is the probability that the first person will collide? 0, that's right. There is no one to collide with, so first person colliding is equals 0. All right, then that probability that the second person is colliding is equals to where n equals 356. That's the number of birthdays we can have. So, oh my God, yeah. You are sharp, that's good. Okay. All right, going back to the question, what is the probability that a second person will collide? 1/365, yeah, 1/n. So basically, out of all birthdays, there is only one we can actually collide with. So that's how we come with the number of 1/n, which is 1/365. Okay. Opposite of that would be probability of second person not colliding is then 1 minus 1 of n, which is 364 over 365, which is approximately 0.997. This is approximately 0.03. Okay, so these are only two examples. Now we want to generalize this to, seeing k people. So if we see k people, so I will write this as general case, k people, then the number of pairs we have between k people equals to k choose 2, which is equal to k times k minus 1 over 2. Okay, that's how many pairs we have. Now we are interested in probability that there is no collision with k pairs. And now imagine that we have whether a given person will collide, like whether one pair will collide is completely independent of whether there were any collisions before. So we are assuming there is some kind of independence here. And then if given that we know that this is the, given that the probability of not colliding equals to 1 minus 1 over n, due to independence, we can just multiply these probabilities as many times as we have pairs, which is k over 2. All right, so what we have employed here is independence. So we know that if their two things are independent, then this thing holds. All right, so Birthday paradox tells us that with k equals 23 people, we should have a probability of collision being approximately 50%. So we have k equals 23 people. Let's plug this into this formula. So we'll have 23 times 22, and this will be equal to 253. Our n is equals 365. And then when we plug in, so let's denote this with star. If we put this thing into star, then we have 1 minus 1 over 365 on the power of 253. We have said before that this is approximately 0.997 power of 253, and that will be equal to approximately 0.467, and that's the probability that no collision will happen. So probability that collision will happen is 1 minus star. So that's 1 minus 0.467, which equals to 0.532, which is close to the number we were looking for. We were looking for the probability of 50%, to say that with k, with the number of people equal to 23, we will have probability of around 50 that there will be collision between the birthday of a pair of people in those 23 people. Okay, so there is a few problems with these, with this specific derivation. Can you identify maybe some of the problems? So remember how I keep saying there's some assumptions are wrong. Yeah, go ahead.
The assumption that all the probability is uniform.
Exactly. Yeah. The problem is with assuming again independence here, and more specifically, what will happen is when you have more people than there are days in a year. So if you have k number of people equal to 366, you know that there must be some collision here in terms of birthdays. However, let's calculate what happens. So the probability of seeing collision with the number of people equaling 366 should be 1, right? Because this must happen. And this is also connected to something called the pigeonhole principle. So this principle says if n items are put in m containers, where n is larger than m, then at least one container must contain at least 2 items. And items in the original forms are pigeons and boxes. And this is a principle that is widely studied in math. So according to this principle, we know that the probability of colliding should be 1. However, when we put, if we here in this derivation, if we put k equals to 366, we will get the value that's very, very, very close to 1, but it's not exactly 1. And that's a problem. So we need to fix this derivation we have and not assume independence. So we will have probability of not colliding. And I will denote this with 2 stars to separate it from the other one. Right, so, sorry, just a moment. I made a mistake. So here we'll have actually probability of colliding. And in this version, we will have again 1 minus. So the probability that the first person will not collide is equals 1, right? Then the probability that the other person will not collide is n minus 1 over n, because there are n minus 1 and n minus 1 options for birthdays one can take to not have collision over all the possible birthdays. Now, when we come to the third person, if we do not want this person to collide with the other 2 people we have seen before, that means we have n minus 2 options for assigning birthday to this person to not have collision. And we will do all of that until n minus last person over n. All right, and a nicer way to write this is like this. And this is more precise way of calculating that probability that there will be colliding, where we didn't assume that these things are independent when, for example, here we have considered that there are n minus 2 possible options given that we have seen 2 people. All right, and now if you put k equals 366 here, you will get the probability of 1 because one of these components will be equal to 0.
I guess the terms like n minus 1 and minus 2, isn't the probability that it's going to collide, like, wouldn't that go up? It's you have more people in the sample instead of like down the probability, because there's like wouldn't the numerator be getting bigger in relation to the denominator?
So I can explain it to you differently. The way to look at this is So you want person, this is the probability that the third person will not collide with other two people.
Oh, so it's like 1 minus whatever.
Yeah, it is a little bit confusing. So basically, what is in the brackets here is probability of not colliding. And then we have 1 minus 1 of probability of not colliding. Yeah, sorry, that wasn't clear enough. Yeah. Okay, and one thing that is going to be useful for you is kind of like a rule of thumb of how many people you need to achieve certain probabilities. So there is this approximation. So the probability given k people is approximately k squared over 2 times n, which means that the number of steps you need to achieve certain probability equals to tau times 2 times n time probability. So let's put some concrete numbers here. If we had n equal 365 and probability equals to 1/2, so 50%, we will have k of 2 times 365 divided by 2. And this number is approximately 19, which is not exactly 23, but it is somewhat close. So this is kind of an approximation you could use to see how many steps you need to achieve a certain probability of seeing the collision. If we had n equals 365 and probability equaling to 1, then we would have k 2 times 365 times 1, and that would be approximately 27, I believe. So this is one approximation you can use, and in the homework, for example, we kind of ask these simulations of these experiments, and you get some concrete numbers by doing these trials, trying to actually get these collisions. And then you get maybe some expectation from your experiments, and you can compare that with the kind of rule of thumb approximation of how many steps you need to achieve certain probability of seeing collision. And then you can compare those two values, and if they seem somewhat close, you can say, okay, this is reasonable to me, and if not, you should kind of look back into your code and see whether you made any mistake. And that's like a general thing to remember, that you will have these guidance, analytical guides to what you should expect, and you will do things by implementing them and then comparing whether the thing you are actually getting computationally matches that analytical expectation is a really good habit to have if you are doing data mining. All right, so if you remember where all of this began, you begin with the question 1, where we ask how many distinct things we need to see to get the collision. And now the answer, you can say, well, approximately this many if we want to have a concrete formula for it. And another thing that is kind of obvious, but I also want to emphasize is that when you're dealing with these random processes, collisions exist, right? So you will, by drawing randomly these people, you will get the collision of their birthdays. Okay, so that's everything I wanted to talk about related to the birthday paradox. Yeah.
Can you explain how you got from what you were doing before, that rule of thumb, like the
Yeah.
2n? That
Yeah, I just jump from one thing to another. So there wasn't any anything you have seen from what I derived before to this the rule of thumb. So there, these kinds of things are disconnected. So it's a little bit funky. I see that, but try to think about it like this. If you have this probability, that's this is the first part here it's a proper derivation of how to calculate this probability. Great. Now you want some approximations to kind of get this number of steps. This thing here doesn't come from it. It is just you can use it as a fact, like this is a rule of thumb people had discovered that you can use for these things. So it is a little bit, I don't know how to write it, but
that as opposed to like the one above it.
The one above it doesn't really give you the number of steps. It just gives you the probability, right? Yeah.
Oh, so we take like that. Okay.
Yeah. Yeah, I don't have momentarily the better way of explaining this. Maybe I can come back to it in the next lecture. For right now, just think about this probability of colliding as a formal way of finding the probability. Kind of, okay, we are done with that. And now there is a rule of thumb of how many steps you need, and that doesn't come from this previous derivation. But maybe the next time I can show how we can actually come to this, how we can derive this number of steps. Yeah, which I don't know by heart right now. Okay, so the next question we want to have is, we want to answer is, when do we see all birthdays? Or in other words, how many people we must see to kind of find a set of people that have all the birthdays in the year. An example that might be closer to your heart is how many Happy Meals you need to buy until you get all the toys that you possibly can get in a Happy Meal. And this problem, like the birthday paradox, has a concrete name associated with it, and that's coupon collector's problem. All right, so let's try to formally answer what is the expected number of items we need to see until we complete an entire set. And one pitfall you might jump into if you are not cautious is to think, okay, I need n items to complete a set of n items. But when we are drawing things randomly, then we might be very unlucky. You might keep buying those Happy Meals and you never get another toy. So how many we need is going to be larger than the actual number of possible items, but let's see how much larger. All right, so again, we are going to have a sequence S1 to SK. And you can think about, let's focus on the example of buying Happy Meals to purchase all the toys. Each one of these items here is related to the event of buying. And then for each one of them, you can have the outcome of whether you get a new toy or you do not get a new toy. And of course, in the first step, you are going to get a new toy, and then maybe in the second one, there is also a good chance you'll get it. And by the third one, you might have, need to have more and more steps until you actually get a new one. So let's introduce some notations that we will need to get the actual formula for how many Happy Meals we need to buy to get all the toys. So with capital TI, we are going to denote the expected number of steps until ith distinct observation. So how many Happy Meals we had to buy until we got the ith distinct toy. And then with small t, we are going to denote the difference between, I'm sorry, this microphone is very annoying. The difference between capital TI and capital TI minus 1. At least it wakes you up a little bit. All right, and this is the expected number of steps one need to take between the I minus 1 distinct and the following. All right, so this is a little bit dry. These are all the stuff we need. So T expected will be expected number of total happy meals we need to get all of the toys. And then to get all of the toys, we need just to sum all of these steps, TIs. This gives us, it's the same way of saying how many in total there are to get all of the toys. So number steps for all toys. Okay. All right, now we want to calculate the probability of seeing ith distinct given I minus 1 distinct observed. And again, as we have seen it in the previous example, this is just the probability of outcomes. So how many are there left to, how many distinct toys there are left? There is n minus I minus 1 of them, because we have already seen I minus 1 over all of the possible toys. And this probability maybe rings a bell to you, and maybe this expected number of steps between two successes also rings a bell. So, and maybe that bell is that TI follows geometric distribution of trial. And maybe that also reminds you that the expectation of a geometric distribution of trials is equal 1 over the, we will call this probability P. So this is how we get the expected number of steps here. And that's going to be just the inverse of this thing, which is n minus n minus. All right. So far, this clear? Okay, I hope the derivation is straightforward. The only little jump is understanding that this follows a geometric distribution, which you kind of just need to know from the previous courses. And then we want to calculate T, which is the total number of steps, total number of happy meals we need to buy before we get all the toys. So, all right, actually what we need is the summation of these expectations. Maybe this is, I jumped too much. So basically what we are doing is expectation of T equals to expectation of sum of I equals n Ti. And then due to the property of expectation, we can put the expectation inside of the sum, which then means that the expected number of total happy meals we need to get equals to this. All right, and we are just going to refactorize that a little bit. We are going to write it, we are going to put n in front of the sum. And if we kind of write this this sum in a more, without making it compact, what you would get is for you would get 1 over n plus 1 over n minus 1 plus 1 over n minus 2, and so on. And another way of writing this is n times I equals to n to, let me just figure out what is the n here. Okay, I forgot what is here. Let's ignore that for now, but basically you can rewrite this this thing here as a summation of 1 over I, where I goes from certain point to the end point, and apologies, I will figure out that later what are the exact points. But this is then this number here. It's called the nth harmonic number. And the harmonic number doesn't have a closed form, but it's, we'll call it Hn, but it has kind of an approximation, which is given by another constant, gamma, plus natural logarithm of n, plus some constant. And this is approximately 0.577. So what this means is that our total number here, expected total number, equals to n times Hn, that comes from here. And that's approximately n times some constant plus logarithm of n, which is approximately, and for us, what we need to remember here is that this is close to n log n. All right, so the question was that we started with was, when do we see all birthdays, or when do we see all of the possible toys that are possible to purchase with a Happy Meal? And if you if there are n such birthdays or toys, then the answer to this question is n log n. Is that clear? Yeah.
Is it worth calculating like a percentage of a chance with a certain number? Like if you're given like 400 people, like what are the chances that you get every birthday? Or are we not gonna go over that thing, or are we going over that?
Probability that you are going to get, so let me see. Yeah, I don't know of it, but that doesn't mean that such a thing doesn't exist. Yeah. Okay, so I want to stop here. Next time I will briefly mention something called probably approximately correct, or PAC, just to make some of these ideas more general, but it's going to be very brief and you don't need to for homework. Don't forget that the homework is due in 7 days. So next Wednesday by 2:45 p.m. it has to be submitted on Canvas. Okay.
Yeah.